Hey, I'm building an operating system that makes it super simple to self-host some common cloud services. This is the very first technical video in the series, which means today we get to set up all the boring stuff. I wanted to get all the project boilerplate out of the way in one video, so this is probably going to be a bit longer than the others, but hey, at least it's easy to skip if you don't care as much about the exhilarating topics like build tools, test frameworks, and code analysis tools. So, with that said, let's get started with the build tools. Alright, so ultimately a build tool takes source code and converts it into an executable. You can do that with GCC in a single command. Amazing, but that kind of begs the question, why? Why should we complicate it more than that? Well, there's a bunch of reasons, but the few that matter the most, at least to me, are build performance, build maintainability, and automation for code analysis and testing tools. The build tool I'll be going with is called Meson. You use Meson by creating a build.meson file in your root directory, running a Meson setup command, which creates a build directory that houses all of the results of your build, and then running Meson compile from within that new build directory. Meson even allows you to create multiple build directories that each have their own flag set, which trigger different parts of the build, but we'll be keeping ours pretty simple for now. All right, let's go use all of this wonderful information to get our build set up. So this segment should be pretty straightforward. All we really got to do is clone the repo. It's just a basic repo right now. It's got a GPL v2 license in it. Nothing too fancy. I'm gonna make our source directory with all of our lovely source code. There. Nice simple hello world. With an extra slash. There we go. So I could just compile it with a straight up GCC and then run it and it works. Voila. But we don't want straight up GCC, that's boring. So what we're gonna do is we're gonna make a Meson build file. We're gonna define project. We'll call this BreezyOS. I don't know, the name doesn't really matter too much at this point. So that's good enough for now. This is gonna create an executable. The executable file will be called Breezy. And for sources, we just have our main.c file. And that should be all we need to do. We've got our Meson build file, we've got our main.c file inside a source. We need to create a build directory with Meson. So that is Meson setup build. We can call the directory whatever we want. I personally like build. You could call it dist or builder or whatever. That's what I'll go for. Go into that directory, and we just say Meson compile, and it should do everything correctly. And now there should be a... Oh, sorry, I called it Breezy. That's why. Haha. And voila, works like a charm. So, given that, let's get this project imported into CLion. And if we look at this, it'll all be good. It correctly detected this as a Meson build. That's all imported now. All right, so one more small thing. We created this build directory, but I noticed that there's also this builder that came out of nowhere. It turns out that's what CLion uses by default, so we are gonna change that. Inside of build execution and deployment, there's this Meson section where we can set whatever build directory we want. Okay, now this should successfully build, which it does. And we should not have that builder anymore, which we don't. Most excellent. All right, so before we get into tests, I actually want to restructure this a little bit. We're going to have some utilities. I want a utilities directory in here. This main meson.build file we have, we're actually going to kind of split this up across directories because each of these subdirectories should really have its own. I'm going to create a Meson build inside a source, and actually another one inside of utils as well. One inside a source, this is going to get our executable. And this parent level one is going to call into source. It's going to list it as a subdirectory. And similarly, the build file inside of source is going to list utils. That should probably happen before we try to build the executable, because this executable is going to depend on these utils. Additionally, we're going to want an includes directory. This is going to have all of our header files in it. We'll namespace them all to Breezy, at least all the stuff that we write. Just going to make an example for now, because yeah, we don't actually have any utility files to create, so that is actually the correct autocomplete. Nice job. So this is just going to define a very simple add method. That's about it. And we'll define its counterpart, which should be pretty straightforward. All right, now we just have to tell Meson about all of these new files. So in the very top level build file, we're going to define a variable, call it global inc for global include. And we'll tell it that include is the name of our include directory that we want to include. So now in our source, we want to add that as an option here. And this variable, even though it's defined in the parent Meson file, is visible in the child ones as well. And I believe it works both ways. So if you define something in the child, the parent can actually see it after the subdir executes. All right, now in the utils Meson build file, this one we want to define basically this utils directory as a utility library that can be imported into other parts of our build. So to do that, we'll just call it utils lib. It's going to be a static library, which means it gets actually built into the code. It's not a runtime thing, it's a compile thing. We'll list the files, which right now is just one. And we've got a similar include directories that we had on, which one was it? This one? Yeah. And that basically says that these utilities also have access to the header files that are in that directory. Now to make other things be able to use it, it's going to be called utils dep for utils dependency. Utils lib is the thing we just created above the static library. And we tag on our favorite include directories here as well. Okay, so I think that's all the build configuration we have to do. So our parent build defines this include directory as global inc, and then it loads the source subdirectory. The source subdirectory loads the utils subdirectory, which defines the static utils library, and then declares it as a dependency so that other pieces of our build can use it. And it also has access to our global includes directory. And then we create the Breezy executable from main.c and include, again, our global includes directory. Now I think we should have access to example utils, but it doesn't appear that we do. All right, so still working on it, but I found a few issues here. Number one, we no longer need the source prefix in front of main.c because this build file is already in the source directory. Number two, we never actually listed the utils dependency as a dependency. But even with those things, I think it's still not quite working. And if I try to run it, it also do not believe can find it at least through here because it's not getting put in our build directory. I'm assuming because it's at a nested layer, but not positive. I'll look into that. I'll get back to you. All right, so half of it was cline being dumb. I can find the import now. The fix to that was literally just close it. I recreated the build directory. I'm not sure if I needed to. And then I just reopened cline again, and hey, it's working. So it's just an indexing issue. The other issue, basically I was trying to run it through cline and it was yelling at me saying I couldn't find the executable. And that's fine. It was because Meson was putting it inside of this build source directory, since that's where this build file resides, which makes total sense. So the two options were basically muck around with cline's configurations to say, hey, look in this other place. Or since this project really only creates this single main executable, I figured I would just throw it into the root level Meson build and put our source prefix back here again. I'm still going to keep this source subdirectory and Meson build file in here. I have a feeling we're going to be adding more things to this. So really it's just the executable here that moved. Continuing forward, let's double check, make sure that we can actually use this add method. I haven't tested that yet. And now we get 3. Awesome. So we've got our include set up. We have at least a placeholder for utility files to go in both our main source directory as well as our includes. And we're able to import things with the Breezy prefix. So now that that's set up, we can move on to setting up some tests, and we'll throw together a very simple test for this utility function that we just created. So there's quite a few different frameworks that all boast a bunch of different benefits, but Breezy's whole thing is trying to keep things simple and fast, preferring libraries that have small APIs and quick runtimes over those that are more featureful. And because of that, I'll be using Unity as my unit test library and FFF, the fake function framework, as my mocking library. Unity is pretty straightforward. You define a C file that contains your tests for one of your source files. That C test file contains a main method that calls into each of your test functions. The main method starts with Unity begin and ends with return Unity end. And between those two calls, you list your test functions inside of a run test method. Each of your test functions has access to a list of assertions that Unity provides us, and those work pretty much the same as all of your other test frameworks would. FFF works alongside Unity, and it makes it super easy to mock functions that the code you're testing needs to call into. That's beneficial for limiting the scope of your tests and making them less brittle overall. You basically just import the FFF header file into your test file, declare which functions you want mocked by using their macros, and it creates a bunch of variables that take the name function name underscore fake. These fake variables give you access to things like call counts, argument lists, and they even give you the ability to set a function's return value. Your build tool, which for us is Meson, creates an executable file for each test file that we write, and then it executes each one and reports back the final results at the end of the build. All right, so the next part of the plan, the big evil plan, is to create a test directory for us to put all of our tests in, get that added to our Meson build, and get the test frameworks installed that we're going to be using. So first up is Unity. I'll take care of that, and then I'll check back in. And then after that, we'll be doing FFF. But for now, let's just do Unity. Okay, so the Unity setup was actually pretty straightforward. Basically just went to their website, jump down to get Unity, download an official release, copy to their GitHub, download the source code. Here's that source code. I unzipped it, which gives me the directory. Jump into source, and it has these 3 files that we care about. So these get copied over to, made this tests directory inside of Breezy, and a Unity subdirectory. And I just copied those 3 files into here. That was all I needed to do to add Unity to the project, but it still needs to actually get executed. We jump back to IntelliJ. And again, here's this tests directory with the Unity files. In our top level Meson build file, we added this tests subdirectory, which runs after our source directory. And then inside of tests, we added this Meson build file. And up here at the top, this is where we configure Unity as a dependency. So this is what loads these 3 files and makes them available for use. And this is a very similar pattern that we did for our utilities. If we jump over to that, you'll see we made a static library pointing it to all of our utility C files. Just one of them, but one is all of them at this point. And then we declared it as a dependency. And that gave us access to use this utils dep variable throughout our build, anything that needs to rely on these utilities. So for Unity, it was very similar. We define it as a static library. And again, it's just that one C file for now that we care about. And then this entire Unity directory gets listed as an include because we've got our 2 header files in here that we want to include. That's all this line does. Once we got our static library, we declare it as a dependency, which makes it accessible to other things to use, specifically our test executable. ultimately, this for each just boils down to running these 2 lines for each file in this list, which is each of our test files. And the 2 commands are basically create an executable from that file and then run the executable. When we're building our test file, we have to list our utilities as a dependency, so that way we actually have access to this add method we've defined. And we also have to list this unity dependency. If we take a look at the BZ example utils, the file that it makes is prefixed with test underscore, followed by BZ example utils, followed by a .c. So that is this file here. You'll see it has a main method, and the way that Unity works is in that main method, you say Unity begin, you execute all of your tests. I only have one, but if I had some other ones, they would look like this. And then you say return Unity end. Unity does require a setup and teardown method to be defined, even if they are no ops. If I were to take these out and try and build, you'll see it fails. It says, hey, cannot find setup or teardown. So we'll make sure to put those in. And then all of our test functions, we only have this one, which tests add. And just for reference, this add method over here is the one we're testing. Pretty straightforward, can't really get any simpler. But we're just saying, use this unity assertion to test that these 2 integers are equal. So we're expecting to see a 3, and we're calling our add method, which we're importing from our utility file. And if we come over here and say run our tests, it runs. It says, okay, 1 passed. Let's say it fails. Let's say, we want to make sure 1 and 2 add up to 4. It will tell us that 1 failed. It gives an incredibly terrifying error message. It's not particularly helpful, but it does say to go check out the test log, which if we do, you'll see this is actually pretty useful. So it tells us file that failed, what line it failed on, function, and the expectation. All right, so that is it for Unity. The next thing I want to add is FFF, the fake function framework by Microsoft. So I'll go get this added. I have a feeling it's going to be very similar setup to what we just did for Unity, and I'll check back in when it's done. All right, so FFF is set up and running. It's relatively smooth, but I already ran into a limitation that I'm not a huge fan of, but we'll see how it goes. Basically, set it up. It was dead simple. You go over to the releases, you download the header file, you put said header file into your repo somewhere. I put it kind of next to my Unity files. Then in my Meson build file for this tests directory, I configured it as a dependency, very similar to what we did for Unity. But since there's no C file, it's just a header file with a bunch of macros and stuff defined. We only need to set it as a includes directory. We don't actually have to create a static library. So once we've done that, we just add FFF as a dependency to our test executable, and it's ready to be used. The problem that I ran into, so if we look up here, I wanted to create a power function to test with Unity and then have it call into a multiply function, which I would be able to mock using FFF. And that's what gave me issues. So when I had both of them defined in the same file, the test was failing to run because multiply was defined twice, once in this C file and once over here where we're telling FFF to mock it. So apparently we can only mock files which aren't being included, which is not ideal. So I basically had to take multiply, move it out to a different C file, and have that get included into my main utility C file. This is all temporary code, so it's not a huge deal. It's just an annoying limitation that I ran into. And again, it makes sense. It's still frustrating. Anyways, to use FFF inside our test, we include the header file and we say define FFF globals. We specify which functions we want to make. In this case, we want to override a multiply function that returns an integer and takes 2 integer parameters. And now anything that calls multiply will use this multiply fake. And this multiply fake, I'm saying it's always going to return a value of 1. Now if I call into my power function with the values of 2 and 3, it should be saying 2 raised to the power of 3. And if we check this out, it's calling this multiply, which we said always returns a value of 1. you look at this code, that means total is always going to have a value of 1, which is why this test passes, which we can see if we run it, passes. Good. Obviously, this is a very contrived example, but the idea was to get the build set up and able to use it, and we did that. It's also good to reset your fakes after you've used them. I didn't do that here, I probably should have. So that's as simple as that. And then there's also this reset history, which clears out some internal FFF structures. Whoops. It shouldn't be the fake, it should just be the main one. So anyways, that's FFF. Next up on my list is to look into adding some code analysis tools to our Meson build. You see, I already have Clang Tidy plugged into CLion, so I'm probably not going to do much configuration for that, but there's a few other tools that I want to look into getting added, so that's next on the list. Code analysis tools typically fall into two main categories. There's your compile time analysis, and then there's your runtime analysis. Compile time analysis is able to find potential issues by inspecting your actual source code, whereas runtime analysis finds issues that occur only while your application is running. You are able to hook up the runtime analysis tools to run during your unit tests to try to catch issues as part of the build process, rather than just relying on manual testing of the final artifacts. I admittedly don't have too much experience with the analysis tools in the C ecosystem, pretty much just the basics of using Valgrind to troubleshoot. It seems like there's a lot of options on the market, but the few that I'll be going with today are Address Sanitizer, or ASAN, Undefined Behavior Sanitizer, or UBSAN, Clang Tidy, and a plethora of compiler flags. I'll also keep Valgrind handy as a manual tool for troubleshooting. Okay, got a few different tools set up. Some of them much more painful than others. I ended up adding a couple and then removing them just because they were proving to be a pain in the neck or catching things that I really didn't care about. But I'll show you what we ended up with. So CLion runs Clang Tidy automatically, which I'm just going to make heavy use of. I'm not going to bother putting it into my Meson build because this is good enough for me. But I did create a Clang Tidy config file in the root of the project. I'll be honest, I don't know what most of this does. I just kind of stole it from the internet. So aside from that, I added a whole bunch of compiler build flags and up here as well, which should catch a lot of things. There's also ASAN and UBSAN, so Address Sanitizer and Undefined Behavior Sanitizer, which Meson kind of has built in. We just have to specify this flag. So if I were to run a build, it will fail, and unfortunately doesn't give a ton of information here in the output. We always have to go up here and check into our favorite log file. And then in here we can see, hey, detected memory leaks at this location. And sure enough, if we go there, I made a malloc with no free, so that's good. So that was the sanitizers. I did have Valgrind on here as well that ran against the tests, but it was conflicting with the sanitizers. We could have created separate build directories, one for the sanitizers and one for Valgrind, but I figured I'll just keep sanitizers as part of the build and use Valgrind if I need it for troubleshooting. So more of a manual tool than an automatic one. I have this wonderful comment here. I spent probably 3 hours troubleshooting. So I was failing to find even a basic memory leak like this one, and it was driving me absolutely insane. And come to find out, it was because I had this debug optimized build type, which behind the scenes sets level 2 optimization. Basically means the compiler removes a bunch of code that's doesn't do anything. So it was straight up removing this malloc before the test even ran. And that's why the memory leak was not getting found. I left a note in here just for future Ben to remember, but for now I'm just going to do regular debug. I don't think I need optimizations at this point when I'm doing production builds, sure, but this is so far into development builds at this point that there's no point in doing optimized builds. I tried adding CPP check as well. That flagged a whole bunch of things in Unity, and I think there might have been some in FFF as well. I didn't feel like sorting through it, and I figured between Clang Tidy and Address Sanitizer and all the compiler flags, I'm probably good for now. So that's the setup, that's what changed, and I think that's it for this video. All right, so we got our build tool in place. We have a placeholder for our utility classes. We have our test framework set up. And overall, a very solid pipeline to make sure that our code stays all spick and span going forward. There's also 2 new note pages on the website that go into slightly different details. You just can't get enough of these very exciting topics. And in the next devlog, we'll tackle displaying something on the monitor. Not anything useful, mind you, but something. And that involves setting up our graphics rendering stack, which makes use of a whole bunch of different Linux libraries, and even gets to apply some of the basics of OpenGL. So if that sounds interesting to you, then stick around. Okay, bye.